Right now, in a city in China, there's a phone network running about 10 times faster than the one you use every day. It is not a plan on paper. It is not a rumor. It is not something scientists hope to build someday. It turned on this year. It runs on real streets, under real rooftops, in a real city full of real people. And it is still running today while you watch this video. But the speed is not even the strangest part of this story. The strangest part is a chip smaller than your fingernail, a chip that can do something no chip on Earth has ever done before. Something so strange that when scientists in other countries read about it, many of them stopped and read it twice just to make sure they understood it right. I'm going to show you exactly what that chip does. I am going to show you why one whole city in China turned itself into a giant test lab. And I am going to show you why some of the richest, most powerful countries on Earth are suddenly spending billions of dollars because they are scared of falling behind. To give you a sense of just how fast we are talking about, the fastest home internet most people have ever used tops out somewhere around 1 billion bits every second, and even that feels like a luxury. The network I am about to show you blows straight past that number using a piece of hardware that fits inside a pocket. But first, you need to understand a problem that has stumped engineers for almost 100 years. Once you understand that problem, everything else in this story will click into place. The race you never noticed. Think about how many times you touched a wireless signal today without even noticing. Your phone used one to load this video. Your car might use one to check traffic. If you went to a doctor this year, some of the machines in that office likely used one too. Factories that build medicine, hospitals that save lives, banks that move your money, all of it rides on invisible signals flying through the air. Have you ever noticed your phone show full bars, yet a simple web page still spins and spins before it loads? Or a video call freezes right at the worst possible moment, right when you needed to hear one important sentence? Those little annoying moments are not random bad luck. They come from real limits packed inside the invisible signals traveling all around you every single day. We will get to exactly why in a minute. Here is something most people never think about. These wireless networks come in generations. You have probably seen the little letters and numbers on your phone screen. 3G, 4G, 5G. Each one of those letters is not just a small upgrade. Each one is a completely different way of sending signals through the air. And here is the part that really matters. Every single time the world jumped to a new generation, it did not just make phones a little faster. It quietly moved money and power to a whole new part of the world. Look back far enough, and you can actually see this happen, generation after generation. When the second generation of wireless networks spread across the globe, the companies building most of the equipment were based in Europe. And those companies grew into giants because of it. When the third generation arrived, a lot of the excitement shifted toward American phone makers, as smartphones started turning into something everyone wanted to own. Then came the fourth generation, and that is when things really exploded because suddenly the United States was not just building phones. It was building the apps that ran on top of them, and that turned into one of the biggest economic booms in modern history. Let me give you one example that shows exactly how big that particular jump was. Before one big jump in wireless speed, sending a single photo from your phone could take a full minute. Video calls barely worked at all. Watching a movie on your phone felt like a joke. Then the network got faster, and almost overnight, everything changed. Apps that could not have existed 1 year earlier suddenly work perfectly. Ride apps that call a car straight to your exact spot. Apps that share photos and videos with millions of people in seconds. Within a few short years, companies nobody had heard of turned into businesses worth hundreds of billions of dollars. Nobody planned that. Nobody sat in a meeting and said, this will happen next year. It happened because the network became fast enough to make it possible. And once it was possible, people built it almost overnight. Now picture what happens when the network gets faster again, much faster. Fast enough for cars to talk to each other in real time and avoid a crash before a human driver could even react. Picture a surgeon sitting in an office in one city, moving their hands through the air while hundreds of miles away. A robotic arm inside an operating room copies every tiny movement instantly, with no delay a patient's safety could ever depend on. Picture classrooms where kids in different countries share the same lesson inside a shared 3D space instead of staring at a flat screen. Picture entire factories running themselves, with machines talking to each other and fixing small problems before a single human worker even notices. That is the dream that the current generation of wireless, the one called 5G, was supposed to deliver. It is not fully delivered yet, and the reason why is a lot simpler and a lot stranger than you might expect. While the rest of the world was still figuring out how to roll out 5G, one country was not waiting around. China built more 5G towers than every other country on the planet combined. By the end of 2025, that number passed 4.5 million towers, with over 1 billion people connected. That is a staggering amount of wireless equipment. And yet, even with all of that in the ground, Regular people were still not getting the mind-blowing speeds that were promised years earlier. Here is why any of this should matter to you personally, even if you never set foot in China. Whatever network standard wins this race eventually shows up inside the phone you carry, the car you drive, and the hospital that treats you, no matter which country you live in. The winner of this race does not just win bragging rights. The winner decides what your future devices are able to do. So somewhere along the way, a group of engineers stopped asking how to build more towers. They started asking a completely different question instead. What if the towers were never really the problem? It helps to remember that a new wireless generation is not just a faster version of the old one, the way a new phone model is just a slightly better version of last year's phone. Each generation is closer to a complete rebuild, using different kinds of signals, different kinds of towers, and often completely different companies leading the way. That is exactly why this next jump is being treated as such a massive deal. Instead of just another routine upgrade nobody will notice, that question is where this entire story begins. And trust me, it gets a lot stranger from here. Before we keep going, if you're the kind of person who likes understanding big changes before everyone else catches on, this is a good moment to hit subscribe. This story is not finished. New pieces of it are showing up every few months, and I plan to keep tracking every single one, so you do not have to go digging for it yourself. All right, let's get into the actual problem. Fast or far, never both. Here is something almost nobody explains simply, even though it explains everything about why your phone works the way it does. A wireless signal is just an invisible wave traveling through the air. Some of these waves wiggle slowly, some of them wiggle very fast. That one small difference decides almost everything a signal can and cannot do. This trade-off has existed since the very first radio message was ever sent across the ocean, more than 100 years ago, and nobody has fully solved it since. Slow, gentle waves are tough. They can travel a very long way. They can pass through walls. They still work when it is raining outside. That is why old-fashioned radio stations could reach listeners from 100 miles away, coming through fuzzy and crackly, but still coming through. The catch is that slow waves cannot carry much information at once. Picture someone banging a huge drum from far across a field. You can hear it from a long distance away, but all you're hearing is a simple beat. You could never use that drum to play someone an entire song, note for note, all the way from that far. Fast, tightly packed waves are the exact opposite. They can carry a massive amount of information because each little wiggle can hold its own tiny piece of data. The problem is that they are delicate. A wall can block them. Rain can weaken them. Even the warm, damp air on a summer afternoon can knock them down. Picture someone playing a beautiful, detailed piece of music, but only through a tiny speaker turned down low. You have to stand right next to it to hear a single note. Take 2 steps back, and the whole thing disappears. Think of it another way, too. A garden hose can gently spray water across your whole yard all afternoon without any trouble. A fire hose blasts an incredible amount of water, more than the garden hose could ever manage, but only for a few feet in front of it before the whole blast turns into useless mist. Wireless waves behave in almost the exact same way. You get either a wide, gentle spray or a powerful short blast. Nobody had ever figured out how to get both from the very same hose. That trade-off, reach or speed, but never both at once, is the exact reason so many people feel let down by 5G. The version of 5G shown off in flashy commercials used the fast, delicate kind of wave. On paper, the numbers looked incredible. In real life, those signals could barely make it 2 or 3 blocks before fading out completely. A single tree in the way could block it. A window could weaken it. Even wrapping your hand around your own phone could mess with the connection. So what most people actually get every day is not that flashy, fast version at all. It is closer to the older, slower kind of wave, just cleaned up a little and given a new label. The little 5G symbol shows up in the corner of your screen, but the real experience underneath barely feels different from what came before it. The commercials made it sound like your phone would get roughly 100 times faster overnight. In reality, most people land somewhere between 200 and 500 million bits every second on a good day. That is a real improvement over what came before it, sure, but it is nowhere close to the future everyone was promised in those flashy launch events. Think about the last time you were packed into a crowded stadium or standing in an elevator and your phone signal completely disappeared. That is the fragile wave problem showing up in your everyday life, even if you never knew what to call it. The signal carrying enough data for a fast connection simply cannot punch through a stadium wall or a metal elevator box, no matter how many bars your phone claims to have. And remember, this was never only about loading videos a bit faster. Cars talking to each other in real time and doctors controlling robotic surgery tools from far away need speeds that are almost unthinkably fast, with almost no delay at all. Regular 5G, the kind most people actually use, does not come close to that. Here's the part that really shows the size of the problem. Even with more than 4 million towers already built across an entire country, the physics did not care one bit. Building another tower is a lot like adding a second garden hose right next to the first one. It helps you cover a little more of the yard, sure, But it can never turn a garden hose into a fire hose. More towers meant more coverage of the exact same limited signal. It did not create a faster kind of signal out of thin air. So the engineers working on this stopped trying to patch the old system. They started asking a bold, almost reckless-sounding question. What if, instead of trying to fix the fragile fast waves everyone already used, they aimed even higher, straight at the fastest, most delicate waves that exist anywhere in nature? Waves so fast and so fragile that, for decades, nobody on Earth had ever managed to use them for real communication, let alone build an entire network around them. To understand why that idea sounded almost impossible, we need to look at what happened next. The chip that breaks the rules. Somewhere far beyond the fast waves used in 5G, there is an even faster kind of wave. Scientists have known about these waves for a very long time. On paper, they could carry an amount of information that makes today's fastest networks look slow by comparison. The problem was, nobody could actually use them. These waves are so fragile that a little bit of moisture floating in the air can weaken them. A single wall stops them cold. Even ordinary humidity on a warm day can knock the signal down to almost nothing. Scientists gave this stuck, frustrating range of waves a nickname. They called it the gap. Hold on to that word because it comes back later in a big way. For years, teams of scientists in the United States, in Japan, and across Europe all tried to close that gap. Picture a locksmith trying to build a key for a lock that melts the moment metal touches it. That is roughly the kind of problem these teams were up against. All of them came away with the same answer. The hardware needed to control these waves simply did not exist yet. It was not a lack of trying, or lack of smart people, or lack of money. It was a wall built by physics itself. On top of that fragile wave problem, there was a second, completely separate headache. Every single wireless system ever built needs different hardware for each different kind of signal, almost like needing a totally different key for every different lock in your house. If you have ever walked past the base of a cell tower, you might have noticed a locked metal cabinet sitting next to it, sometimes several of them lined up in a row. Inside those cabinets sit rows of equipment, tangled cables and humming cooling fans, all working nonstop just to keep one single tower running. A real wireless tower is basically a stack of separate boxes bolted together. One box for slow signals, another for medium signals, another for fast signals, each one with its own parts. That setup works, but it is bulky, expensive, and complicated to build and repair. Now, here is where the story turns. A team of scientists working at Peking University and the City University of Hong Kong found a way to solve both of these problems with one single idea. Their work was published in September 2025 in Nature, one of the most respected science journals in the entire world. Here's the trick. And it is genuinely clever once you hear it explained simply. Instead of handling every kind of wireless signal using separate electronic parts, their chip turns the signal into light first. Picture a signal landing on the chip as a normal electric wave. The chip grabs that wave, turns it into a tiny beam of light, sends that light zipping down a path barely wider than a human hair, and then flips it back into a normal wireless signal on the other end, all before you would ever notice a delay. It processes the signal while it is still light, then turns it back into a normal signal at the very end. Why does that matter so much? Because light does not care what kind of signal it is carrying. A beam of light can carry a slow signal, a fast signal, or even one of those impossible waves from the gap, all using the exact same path. It is like discovering one universal key that opens every single lock in the house, instead of needing 9 different keys jammed onto one key ring. Light works so well for this job because of something you probably already know without ever thinking about it. Beams of light do not crash into each other the way cars do on a crowded road. Different colors and different beams of light can travel side by side down the exact same tiny path without getting mixed up or slowing each other down. That is exactly the kind of order engineers needed to finally control every type of wireless signal using one shared piece of hardware instead of 9 separate ones. This was not a project built by one country working alone in secret either. Researchers from the University of California in Santa Barbara helped test parts of the design too, which shows this breakthrough came from scientists working across borders, all chasing the exact same idea from different directions at once. And the size of this chip is almost hard to believe. It is about 11 millimeters long, which is shorter than a standard paperclip. It is less than 2 millimeters wide, thinner than a piece of spaghetti. You could balance it on the tip of your finger. Yet that tiny sliver of material can handle 9 completely different kinds of wireless signals, all on one single piece of hardware. That means one chip can now handle everything from the huge, gentle waves used to reach ships far out at sea, all the way up to the tiny, delicate waves sitting right at the edge of what science can currently control. 9 separate equipment boxes that normally sit inside a wireless tower, replaced by one chip smaller than your fingernail. In testing, the chip pushed data at speeds over 100 billion bits every single second. To put that in a way that actually means something, that is fast enough to download 2 extremely high-quality movies in about 1 second. And it could switch between totally different types of signals in under 200 millionths of a second. That is faster than the blink of an eye, faster than you could even notice it happening. Think about what that means in the real world. If a chip the size of a fingernail can replace an entire closet full of equipment, then building a wireless tower suddenly becomes cheaper, smaller, and far easier. A rooftop antenna that once needed a room full of gear could shrink down to something the size of a shoebox. Imagine every streetlight, every bus stop, and every rooftop across an entire city being able to double as a small wireless tower, simply because the equipment finally got small enough and cheap enough to tuck almost anywhere. Building and running a single traditional cell tower can cost a company well over $100,000 once you add up the equipment, the cooling, and the electricity bill that never stops. Shrinking most of that down to one small chip does not just save space. It could save companies staggering amounts of money over time, which usually means the savings eventually reach regular customers too in the form of cheaper phone plans and faster rollouts in smaller towns that normally get the newest technology last. Multiply that across millions of towers, and you start to understand why scientists everywhere took notice. There's one more piece that is easy to miss, but might be the most important part of all. Because this one chip can now handle the tough, reliable slow waves and the fast, fragile waves from the gap at the exact same time, on the exact same piece of hardware, the old trade-off starts to disappear. Fast or far, pick one, stops being a forced choice for the very first time. A chip working perfectly inside a lab is one kind of achievement. Turning that idea into something an entire city can actually use is a completely different challenge. And that challenge is exactly what happened next. The city running faster than anywhere else. Before this story reaches a whole city, it helps to know that the fragile, impossible waves from the gap had already proven themselves outside a lab more than once. Back in January 2022, a research team in the city of Nanjing sent a real signal, not a projection, not a guess, straight through open air using these delicate waves. It reached over 200 billion bits every second, a world record at the time for that kind of signal. This was not a quiet number buried inside a research paper nobody read. Engineers around the world took notice because, for the first time, someone had proven the gap was not truly impossible. It was simply unsolved. Less than 2 years later, near the end of 2023, the very same team broke their own record. This time, they crossed 1 trillion bits every single second, using the same fragile waves almost everyone else in the world had given up on. Those were real, independently confirmed tests, not just numbers on a slide in a meeting room. They proved something huge. The gap could be crossed. It just took the right hardware. Then came the chip breakthrough from September 2025, showing exactly how to combine every kind of signal, fragile and tough alike, onto one small, affordable piece of hardware. This live city test did not appear out of nowhere either. Government-backed trials had already been running quietly behind the scenes for years, producing a reserve of more than 300 separate pieces of working 6G technology before Nanjing's network ever went live. By the time the city network turned on, a second, deeper round of testing was already underway, building directly on top of everything those earlier trials had already proven. Put those two pieces together, and you get the moment this entire story has been building toward. On April 21st, 2026, engineers turned all of this research into something you could actually walk underneath. In the city of Nanjing, 10 wireless towers switched on together, forming the very first pre-6G network ever built inside a real living city instead of a sealed-off lab. Early tests showed speeds up to 10 times faster than a typical 5G connection. This was not locked away behind laboratory doors. It was running through real streets, past real apartment buildings, through real weather. And it was not just fast for the sake of being fast. Real applications were already running on it. Picture a drone hovering beside a tall bridge, streaming crystal clear video back to an inspector's screen with zero noticeable delay, checking for cracks that would normally take a person hours to spot by climbing up there in person. Picture a factory floor where a robotic arm receives a wireless command and moves instantly, just as fast as if it were connected by a physical cable plugged directly into the wall with no lag between the order and the action. And picture a video call where the other person does not just appear on a flat screen, but shows up as a three-dimensional image standing right in the room with you, close enough that it feels like they walked in through the door. Engineers were also testing something they call embodied intelligence, which is a fancy way of saying robots that can sense and react to the real world around them, not just follow a fixed set of instructions. Picture a warehouse robot rolling down an aisle, spotting a box that fell on the floor and instantly rerouting itself around it, using wireless commands sent and received faster than the robot's own wheels could physically move. None of that is a future promise sitting on a slide somewhere. It is running right now in a real city while you are watching this video. For most people actually living in Nanjing, all of this probably looks completely ordinary. They walk past construction cranes, wait for the bus, and grab their morning coffee with no real idea that the invisible signals passing through the air around them are years ahead of what almost anywhere else on Earth is currently using. The city backed this project with $485 million through something they called the Nanjing 6G Future Industry Fund. The goal is bold and simple: turn Nanjing into the very first true 6G city on the entire planet. And this was not some small local project either. Some of the biggest names in wireless technology on Earth, including Huawei, Qualcomm, China Mobile, and Ericsson, were all involved in building it. Nanjing was never meant to be the finish line either. It was built as a working proof, a place engineers could test real problems in a real environment before trying to copy the idea across other cities. If the lessons learned from these 10 towers hold up over time, there's nothing stopping the same approach from spreading to dozens of other cities within just a few years. A single city lighting up like this does not stay quiet for long. And once the rest of the world saw exactly what had happened in Nanjing, everything sped up and fast. Who gets to write the rules? The moment other countries saw what China had pulled off, money started moving everywhere, almost like the early days of a space race, except this time the finish line was an invisible signal instead of a rocket. By early 2026, the total amount spent worldwide on 6G research crossed roughly $20 billion. China, the United States, and South Korea together made up around 3 out of every 4 of those dollars. South Korea alone committed several $100 million toward its own 6G push, aiming to have a working pilot service ready by 2028. Japan and the United States began teaming up on a joint 6G research plan of their own. Across Europe, multiple countries poured money into their own separate 6G research programs, hoping not to be left behind. But money alone does not decide who ends up leading a technology like this. There is something else involved that sounds boring on the surface, but might actually matter more than the speed records or the fancy demonstrations. It is called a patent. A patent is basically the official, legally protected instructions for how something works or how it gets built. If a company or a country holds the patent for an important piece of technology, everyone else who wants to use that technology usually has to ask permission and often has to pay for it. Imagine if one single company had owned the patent for the wheel itself, and every car maker on Earth had to ask permission and pay a fee just to use round wheels. That is roughly the kind of leverage a huge share of patents can create. Except this time, it is happening with a technology that every phone, tower, and network on the planet will eventually run on. As of the most recent count, China holds about 40% of every 6G patent filed anywhere in the entire world. That is more than the next several biggest countries combined. Here's why that matters so much. The official rulebook for how 6G actually works has not been finished yet. Engineers from countries all over the world still need to agree on the final standards, and that agreement is expected to be locked in around 2028. In 2027, an international conference is also scheduled to decide how the fastest, most valuable airwaves on Earth get divided up between different countries, almost like dividing up empty lanes on a highway before anyone is allowed to drive on them. Whoever walks into those meetings holding the most patents, the most real-world proof, and the most working technology ends up with the loudest voice in the room. And the country with the loudest voice tends to shape the rules that every single phone, tower, and network on Earth eventually has to follow. For someone just trying to buy a new phone or pay a monthly bill, all of this might feel far away and unimportant. But rules like these tend to trickle all the way down eventually into the price of the phone in your pocket, into which company builds the equipment your carrier depends on, and into which apps run smoothly on your specific network and which ones do not. Think about airwaves like empty lanes on a giant invisible highway that circles the entire planet. Right now, a lot of those lanes above a certain speed limit have never been assigned to anyone. The 2027 meeting is essentially where every country on Earth sits down at the same table and decides who gets which lanes. Once a country is handed a lane, building the towers and equipment to actually use it becomes far easier. And pulling ahead in that meeting can lock in an advantage that lasts for years afterward. Remember earlier when we talked about how each new generation of wireless quietly shifted power to a different part of the world? Older networks shifted power toward Europe. Later ones shifted it toward the United States, where the app economy exploded and grew into an industry worth hundreds of billions of dollars. This new generation looks like it could shift that center of gravity somewhere else entirely, for the first time in the history of wireless technology. Now, to be completely fair, this story is not all smooth sailing, and it deserves an honest look at the problems too. It is worth staying a little skeptical here. Lab records and small pilot projects do not always turn into something the average person can actually use for years, sometimes even a decade later. Plenty of exciting technologies have stalled out somewhere between an impressive headline and an actual product you can buy in a store. Those same fragile, ultra-fast waves from the gap are still fragile, even inside a working city network. They still cannot pass through solid walls. they still get weakened by rain and thick humidity in the air. Covering an entire city with them could mean placing antennas on nearly every building, not just every block, which costs an enormous amount of money and a huge amount of electricity to keep running around the clock. There are real political tensions too. The United States, the United Kingdom, and Australia have already banned Huawei equipment from their own 5G networks over serious security concerns. Those same tensions are almost certainly going to follow this new technology into 6G, meaning some countries may end up refusing Chinese-built equipment entirely, splitting the wireless world into two separate paths instead of one shared one. On top of all that, there simply are not enough skilled people to build this technology quickly anywhere on Earth. Building 6G takes experts in wireless engineering, artificial intelligence, advanced materials, and manufacturing, all working together at the same time. China itself has openly admitted it does not have enough of these specialists yet. Neither does anyone else. This is not one field of study. It is a dozen fields, all colliding together at once, and there are only so many people alive right now who understand all of them well. Some of the oldest, most respected wireless companies in the world, companies that helped build 2G and 3G decades ago, have started openly admitting that the center of wireless research is shifting somewhere new. That kind of admission from companies that used to lead the entire industry says a lot on its own, even without a single speed test to back it up. None of those problems erase what has already happened, though. A real pre-6G network is genuinely running through a real city today. A working chip smaller than a fingernail really can merge 9 different kinds of wireless signals into one. And for the first time in wireless history, the biggest share of the patents, the biggest real-world speed records, and a live functioning network are mostly sitting inside one single country at the same time. The countries that show up to the big international meetings with real working results are going to shape those decisions for decades to come. The countries that show up with nothing but slideshows and promises are mostly going to be along for the ride. There is a reason falling behind early in a race like this tends to matter so much. Once a country's equipment, chips, and software get built into the official global rulebook, switching away from it later becomes incredibly expensive and complicated for everyone else. Countries that show up late are not just a little behind. They often end up buying someone else's equipment, following someone else's rules, and paying someone else's licensing fees for years afterward, simply because the early lead was never caught in time. That is not a guess about the future. Based on everything happening right now, it is simply the direction all of this is already pointing. So that is where things stand at this very moment. A tiny chip that thinks in light instead of electricity. A real city already running on signals that most of the world once believed were impossible to use. A trade-off between speed and distance that lasted for over 100 years, finally starting to crack. And a race between some of the most powerful countries on the planet that is only just getting started. If this video helped you understand something huge in a simple way, go ahead and tap that like button. It genuinely helps this channel keep making videos like this one. Hit subscribe and turn on notifications too, because this story is moving fast, and I plan on covering the next update the moment it happens. Here's a question I would love to hear your answer to in the comments. If the country that builds the fastest network also gets to write the rules everyone else has to follow, do you think that is fair, or do you think it should work differently? And if you want to understand the bigger fight over the tiny chips that power all of this, go check out the video I made covering that story next.